Hey space explorers and curious minds, welcome to our super mega video, where we'll dive into one of astrophysics' craziest mysteries. What are white holes? Buckle up for a thrilling ride filled with mind-blowing facts, a dash of cosmic imagination, and plenty of wow moments. But before we blast off, make sure to smash that like button, subscribe to our channel, and share this video with everyone who loves stargazing and space mysteries. Introduction. Why white holes deserve your attention. You've certainly heard of black holes, those gravitational beasts that swallow everything that strays too close and don't let any light escape. But imagine there's a cosmic mirror image of a black hole that does exactly the opposite, spits out matter and energy instead of gobbling it up. These theoretical objects are called white holes, and they completely flip our intuition about how gravity and space-time work. Today, we'll explain what scientists mean by a white hole, why none has ever been observed, and what their existence, purely hypothetical as it may be, could mean for our understanding of the universe. Strap on your starship captain's hat, it's time to take off! What exactly is a white hole? A simple breakdown picture, pausing a documentary about black holes and then reversing the footage. Instead of seeing matter and light getting sucked in, you'd see streams of material bursting outward like fireworks. That's the basic idea behind a white hole. Rather than being a one-way drain, it's a one-way fountain. In theory, a white hole has an event horizon, just like a black hole does. But in reverse, nothing can enter a white hole. Everything inside is forcefully ejected outward. Sounds wild, right? But here's the big catch. While this concept is perfectly valid in certain mathematical solutions of Einstein's general relativity equations, reality quickly complicates things. Let's look at why. Theoretical roots. How white holes emerge on paper. When physicists solve Einstein's field equations for gravity under idealized conditions, no charge, no rotation, they discover two mirror image solutions. One solution describes a black hole that swallows matter. The mirror image solution describes a white hole that only expels matter. In this perfectly reversed scenario, all the material that entered a black hole in some other region of space-time would pop out of the corresponding white hole. It's like time reversing a black hole's process, but as soon as you try to connect those dots to our real universe, major obstacles pop up. Instant instability. If anything tries to fall into a white hole, even a photon of light, the equations flip back and turn it into a black hole. In other words, a white hole can't sustain itself once it interacts with external matter or radiation. Thermodynamic headaches. A white hole would decrease entropy by suddenly spewing out matter and energy, violating the second law of thermodynamics. That order from chaos scenario isn't something our universe allows. So, while white holes are mathematically intriguing, they can't survive in a physically realistic setting. They collapse or vanish before you can even blink. Why no one has ever seen a white hole scanning the skies for cosmic spurts? Astronomers have been scanning the cosmos for decades using X-ray and gamma-ray telescopes, radio arrays, and optical observatories. They look for any sign of a super bright source that seems to eject matter and energy in a fountain-like eruption. Instead, what they find are supernovae, neutron stars, pulsars, and active galactic nuclei, objects that obey familiar physical laws. A genuine white hole would have to appear as a point source bursting out material in all directions, and nothing like that has ever been catalogued. Clashing with entropy and energy conservation, a true white hole would be like a cosmic cheat code. It spits out matter and energy without ever taking anything in. That concept directly clashes with how energy and entropy behave in our universe. If a white hole really ejected stuff, it would be reversing the usual increase in disorder, which conflicts with the second law of thermodynamics. No wonder our telescopes haven't found so much as a hint of a white hole. Our universe simply won't play along with such an absurd scenario. White holes as wormhole exits. Sci-fi or semi-plausible? Wormholes. Tunnels through space-time. One tantalizing idea is that a white hole might be the exit of a wormhole, while the entrance is a black hole somewhere else. A wormhole is a hypothetical shortcut through space-time, a tunnel connecting two distinct regions. In this picture, entrance, black hole. Everything that falls in lands in a singularity. Tunnel, Einstein-Rosen bridge or wormhole. A warp in space-time connecting the entrance to an exit. Exit, white hole. Matter that traveled through the tunnel pops out here, possibly light years away, or even in a different cosmic epoch entirely. The exotic matter snag. For a wormhole to remain open, you need a bizarre kind of exotic matter with negative energy density, something no one has ever detected. Without that exotic matter holding up the tunnel, the wormhole pinches off the instant it tries to form, collapsing into a regular black hole. In practice, that means the entrance and exit vanish before you can send anything through. Until we find or create exotic negative energy matter, wormholes, complete with white hole exits, remain pure mathematical fantasy. White holes and the Big Bang. A head-spinning speculation, the Big Bang is a super white hole. Some cosmologists have even suggested that our entire universe might have started as a massive white hole inside a parent universe. In this speculative picture, a colossal amount of mass in some prior universe collapsed into a black hole. That black hole then connected via a wormhole, and our Big Bang was the fountain of that white hole on the other side. This would neatly explain why the universe appears so homogeneous and why it all began simultaneously. But this hypothesis runs into immediate snags. Where did the parent universe matter come from? If our universe emerged from a white hole, there must have been another universe feeding that white hole, and so on ad infinitum. Information paradox. If the white hole spewed everything out, how is information conserved? We know entropy at the moment of the Big Bang was extremely low, which is hard to reconcile with a white hole's properties. Despite these challenges, the idea is an exciting mental exercise. It pushes theorists to explore new frameworks that might better unite gravity, quantum mechanics, and cosmology. Tiny, fleeting white holes. Quantum fluctuations in action, microscopic bursts in quantum foam. At the quantum scale, space-time isn't smooth. It bubbles up in tiny, rapid fluctuations. Some physicists speculate that microscopic white holes might appear and vanish in these quantum froths, immediately converting to mini black holes in a flash. To us, macroscopic beings, such blink-and-you-miss-it events are completely undetectable. They'd be far smaller than anything our most powerful colliders or detectors could see. Lab experiments chasing mini black holes and massive particle accelerators like the Large Hadron Collider, LHC. There were hopes that high-energy collisions might create a tiny black hole, which could then briefly act like a white hole before evaporating via Hawking radiation. If such phenomena occurred, they would reveal crucial clues about how gravity and quantum mechanics mesh in extreme conditions. So far, though, no experiment has seen any evidence for microscopic black or white holes. Why do scientists even study white holes? Pushing general relativity to its limits, white holes force us to probe the boundaries of Einstein's theory. By asking, why can't a white hole exist, we learn about the cracks between general relativity and quantum mechanics. Any insight into why white holes are theoretically allowed but physically unstable might guide us toward a more complete theory of quantum gravity, driving technological innovation. Even though white holes haven't been observed, the quest to find them has spurred real-world advances. X-ray and gamma-ray detectors have become ever more sensitive, opening windows to previously unseen cosmic phenomena. Gravitational wave observatories like LIGO are designed to pick up on exotic space-time ripples that might accompany fleeting white hole events. Supercomputer simulations. Modeling extreme gravity regimes help us understand not only white holes, but also neutron stars, black hole mergers, and the early universe. In other words, chasing white holes makes us smarter about astrophysics as a whole, even if we never find a single one. What would happen if you actually encountered a white hole? A Hollywood-style science fiction scenario? Imagine you're piloting a starship on the edge of a distant galaxy when suddenly your scanners light up. Extremely bright X-ray source detected. You approach cautiously and discover a glowing, whirling vortex of energy like a space waterfall. As you get too close, harsh gamma rays and ultra-relativistic particles slam into your shields. Alarms blare, systems overheat, and your ship is hurled away by the sheer intensity, because this white hole is spitting matter and radiation at near light speed. In a blink, you realize that instead of falling in, everything around you is being violently ejected. Real-world implications for physics. If astronomers ever did spot an object that behaved like a white hole, they'd scramble to analyze the high-energy emissions, spectrum, particle speeds, mass flow, to see how it matches theoretical predictions. Physicists would immediately revise or refine general relativity models to account for this reverse black hole, likely shaking up our understanding of energy and information in extreme gravity. If it turned out to be the exit of a wormhole, science fiction would become science fact. We'd have an actual intercosmic portal, opening up wild possibilities for travel and communication. Realistically, though, the chance of stumbling upon a stable macroscopic white hole in our galaxy is effectively zero. Nevertheless, the thought experiment itself sparks incredible ideas in both science and fiction. 10 jaw-dropping facts about white holes, mathematical twin of a black hole. In Einstein's field equations, you can flip a black hole solution to get a white hole solution. Yet that white hole is unstable as soon as it interacts with anything. One-way ticket out. For a white hole, the event horizon works in reverse. Matter and light can only exit, never enter. Potential wormhole exit. In theory, white holes might be the other end of a wormhole tunnel whose entrance is a black hole. Big Bang speculations. Some cosmologists propose our Big Bang might have been a white hole eruption in another universe, but evidential proof is non-existent. Quantum foams. Tiny white holes may appear fleetingly in quantum fluctuations of spacetime, then collapse to micro-black holes before disappearing, completely invisible at earthly scales. Entropy paradox. If a white hole ejected all that mass and energy, it would reduce entropy, violating the second law of thermodynamics. Our universe simply won't allow that to happen on macro scales. No candidates so far. Despite billions of observations by X-ray, gamma-ray, and gravitational wave detectors, no known cosmic object behaves like a white hole. Technology boons. The search for white holes drives improvements in high-energy detectors and gravitational wave observatories, benefiting all of astrophysics. Sci-fi goldmine. White holes appear regularly in science fiction stories as dramatic cosmic ejectors or wormhole exits, inspiring filmmakers and writers. Future discovery potential. If anyone ever finds a white hole, it would revolutionize physics, forcing us to rewrite general relativity, quantum theory, and our understanding of spacetime. Summary. Why white holes ignite our imagination. White holes remain a fascinating boundary case in astrophysics. They're the theoretical mirror image of black holes, expelling instead of swallowing. In our universe, they're so unstable that any attempt to feed them even a single particle will turn them into a normal black hole. No observations to date match a white hole's expected signature, so they remain purely hypothetical. Studying them pushes us to probe quantum gravity, advanced detectors, and new simulation techniques. From a pop culture standpoint, they're thrilling cosmic fountains and potential wormhole portals, pure inspiration for filmmakers and dreamers. Even if white holes only live in equations, they remind us how little we truly know about gravity, entropy, and the fundamental structure of spacetime. Each new thought experiment or simulation about white holes could be a step toward the grand unification of physics that Einstein and his successors never quite nailed down. We want to hear from you! Which of the 10 facts about white holes blew your mind the most? Do you think we might one day see evidence of a fleeting microscopic white hole in particle collisions? Would you dare pilot a ship near an object that expels matter at near light speed? Drop your thoughts and questions in the comments below. And if you loved this super mega fun and fascinating dive into white holes, be sure to hit like, subscribe for more cosmic mysteries, and share this video with anyone who gazes up at the stars in wonder.